All right. So hopefully you've all encountered that situation where you go swimming and you put a beach ball underwater and you hold it down and then you let it go and the beach ball launches forward and smacks you in the face. You know what I'm talking about?
Too many times.
No, every time I'm in the pool. Even if I don't have a beach ball, I get smacked in the face.
Exactly.
So let me ask you this. Do you think that the acceleration of the beach ball traveling up was faster or slower than the speed at which things, or the acceleration at which things fall? Think about that for a second. So does it feel like the beach ball launching towards your face was faster, slower, or the same speed at which things fall? In other words, faster or slower than 10 meters per second squared? Faster? Slower? Same? Okay. Well, it's kind of interesting. So this is what we're going to do. You can actually figure out whether it is faster or slower, because zoom tight. This is what I want you to think about. Imagine you hold a plastic block underwater. The plastic block has a density of 750 kilogram per cubic meter. So in other words, it's a floaty. Okay. What's the density of water? 1,000. So the density of our friend water is 1,000 kilogram per cubic meter. Okay. Again, we should really move towards using standard units away from kilogram per liter and gram per milliliter towards standard units of kilogram per cubic meter. You probably also noticed your packet does that too. So imagine you're holding a block of plastic underwater, and then you remove your hand. What's the block going to do? By shoot up, you mean it's going to accelerate upward, right? Yes, using physics terms, shoot up means it's going to accelerate upward, and I want to know how fast it's going to do that. So, there's water, there's our block. The block has a density of 750 kilogram per cubic meter. What is the mass of the block? That's not a number. We're working on a number. Sex? X. No, just give me a number. 10. Okay, so our block has a mass of 10 kilograms. Wow. I'm just burning through my pens. Okay. Can you see this in the back? Okay. So the block has a mass of 10 kilograms and a density of 750 kilograms per cubic meter. So when the hand is removed, it's going to accelerate upward. I want to know how fast. What will be its magnitude of acceleration? So let's start this. When something accelerates downward, what's causing it to accelerate downward? Gravity. When something accelerates upward, what causes something to accelerate upward? Yeah. So there's two forces that are working. One thing's pulling it down, and one thing's pulling it up. What's pulling it down? G. What's pulling it up? FB. So let's think about some possible answers. Throw out some answers that you think might work. 6. 6 units. 6 girth units. 6 what? 6 meters per second squared. What else? So basically, you're convinced it's going to go slower than gravity. 12? Okay. Yeah, just draw some numbers. 24. 10? Ah, there we go. Now we're thinking. Okay, maybe it's exactly the same as gravity. Okay, so we have a plastic block. We have a plastic block with a density of 750 kilograms per cubic meter and a mass of 10 kilograms. First group to get the answer correct gets cookies or fruit snacks. Your choice.
Oh no. Oh man.
A plastic.
Let's say a maximum of 3. Yes. So you figure out with what acceleration should it move. I already know the answer because you picked the same mass that 3 and 4 did. And no texting anyone from period 4. That would be cheating. Okay. Is that your correct answer? Is that your answer?
Yeah.
Okay. So when you have your answer, come up here and just write your answer down, your name or your group. So Briggs, DJ, and Taylor are saying 10. Maybe it's right, maybe it's not.
Hey! Me too.
Daniel, I thought you were going to get the correct answer. Okay. You want to put yourself in the group with the bad answer? Or
Did you hear what I said earlier? And you thought I was going to get the correct answer from that?
Oh, okay. No, it's not then. But, you know, that was fun. Okay. But how about we do some math and figure out what the acceleration would be? Okay. Excellent.
I thought that said its density was 750. So we have to do density divided by mass, or
I don't know.
density divided by mass gets you what I think, right? So it's like 75.
Yes.
Because it's D equals MV. But you don't.
Good.
We just have to do it be the same. We just have to do 10 times 10 to get the 100 for our yeah. So we know for sure it's going to be minus or 100 minus something. 10. And we're of course buoyant.
Yeah, go ahead.
Isn't it just 1 gram per meter? Well, it's 25.1 gram.
Oh. Meter per second squared, yes, please.
Wait!
Well, I'm just putting a line. Oh, Tate, I'm sorry. There I go again. Hey, there we go.
You did it intentionally.
Trying. What? Water. Alright, Michael's up. It's all over now. Wow.
Wait, so whoever gets it right or whoever gets it first? Oh, whoever gets it right first. Oh.
In theory, if I were to write an answer above all of theirs,
I think we'll remember.
It's 75.
It's the fair.
what if I just do like an amnesia card all over the room without running gas now?
That might work.
So like the weight of water displaced the
See, I
weight
was
of the
thinking
ice.
that, but then I just get
Or 75% with the weight of the caustic soda. Or 75% anyway.
Okay,
75% of 10. only do 100 minus that, can't we? Would that work or no? Well, then they have it up there.
Do you know my name?
Hey. Hello.
So did you got that right? Are you kidding me?
Block out the present volume and use volume to find out that force is placed.
Oh,
I gave you the point.
Hey, but you wrote yours
you
after.
changed. I'm thinking.
Let's take a couple more minutes and then we'll move on.
No. Volume is 0.01. I don't think it's the right answer.
Right, like better than nothing.
Sometimes nothing is better than something.
Okay, I was gonna put 7.5, but I didn't think that was right.
What?
I was gonna put 7.5 actually.
Wait, no, Aaliyah. You would have to do density, so you have to do 750 times 10 times 75. And you
That's
get
what I should say.
that number. So you would have to, what you have to do, like 100
I will put up with
minus that number divided by 10 divided your acceleration.
That's the volume. It is.
On the answer?
there right now.
I'm thinking the same thing as you guys.
Yeah, that's the exact same thing now.
Hey, Simone, move the decimal place to 0.13.
Okay, so look.
0.13? That's so slow.
I don't know.
Okay, so the point.
I don't know. That doesn't make sense anymore. Yeah, there you go.
Well, this block does have a density 3/4 out of water.
Yeah.
Okay, so yeah, once the move's done, we're gonna move on. The correct answer is up there.
Oh, well.
Okay.
It's up there too, but is that the answer I have?
It's very shiny, but I think it's not in the face. It was 13 more.
Okay, here we go.
You know what, if I get it wrong, it's the decimal place.
I hope it's 13.36.
Because I did it.
Okay. All right. So, ladies and gentlemen, so there's basically two force vectors involved, right? We have the weight of the block pulling down and the buoyant force of the fluid pushing up. And we remember that when we care about acceleration, we like to use Newton's second law, or F equals ma, but we need to change it and realize that A is F over m, and what's the F? F, one more syllable, F net. F net, okay? So the acceleration is the F net over the mass. And we know the F net is going to be the force of buoyancy minus the force of weight over the m. So far, so good? Because it's pulling down.
I know.
Yes. Would you like me to put a plus or minus for the absolute value? But we know in this case, since it's plastic, it's going to have more, and it's underwater, it's going to have more buoyant force and it's going to have weight. So that's great. So let's look at the variables that we're using. The first one that's really easy is Fg. What's Fg? 10 times 100 newtons. Okay, it's just mg, which is 10 kilograms times 10 meters per second squared, or 100 newtons. So gravity's pulling the block down with 100 newtons. So the big question is, how much is the fluid pushing back? We remember, because from Aristotle, or Archimedes, that buoyant force is equal to the Fg of the H2O displaced. Okay, so the water displaced. So we got to find out what the water is, how much water gets displaced. How do we do that? Exactly. Use the density to find the volume. Find the volume, right. So density is mass over volume. So since it is, then volume is what over what? Mass divided by density. And since I'm just, cruising along, I'm also going to write that mass is what times what? Density times volume. That's going to be important for something we're going to be using later. Okay, so we need to figure out the volume displaced, and the volume of the H2O displaced is going to be the volume of the block, which is just mass over density. So 10 kilograms over 750 kilogram meter per second cubed. So what's the volume of the block? 0.013 cubic meters. Okay. Did we have to round it all, or is it just 0.013?
It's 3. Yeah, there you go.
I know what the correct answer is because you guys chose the same mass as period 4, which is great for me. So anyway, so there's the volume. Now we need to figure out the mass of the water. So the mass of the H2O is just what?
1,000.
Yeah, so density times volume. So 1,000 for the density times 0.01333 and so on cubic meters, which means the mass is about what?
13.3.
Yeah, it's about 13.3 kilograms. Okay, we're almost there. So now we need the Fg of the H2O. How do I turn a mass into a weight? Multiply by 10. So that's about 133 newtons. So the buoyant force equal to the weight of the water displaced is about 133 newtons. Yay! Okay, so F net is, you don't like this? I don't like this math thing. Math. You don't have to use math after class, or after high school. You can do things that don't use math. I'm sure there's something. I'm sure there's some career out there somewhere that doesn't use math. Nothing immediately comes to mind, but I'm sure there's something out there that doesn't use math. No, they still want to be able to calculate how much money they should make. So if you're like, well, if my route is 200 miles, and to this year I did 230 miles, I should be able to make this much money.
But they don't have to care about that.
They'll just accept whatever paycheck they get.
Yeah.
Let's go with that. Okay. So moving on. Yeah, we're just gonna assume your boss will just pay you what you deserve and never shortchange you.
Yeah.
Okay. Well, good luck.
Good luck.
So anyway, so the buoyant force is 133 newtons minus the weight of 100 newtons. So the net force is how much? 33 newtons. The mass is 10 kilograms. And who got the correct answer? Michael and James. Do you want cookies? Do you want oatmeal craising cookies or fruit snacks?
Taylor, DJ, what was the first thing I said? I said it's gravity minus the, or it's gravity over the buoyant force. And negative gravity plus the buoyant force. That's the answer.
Anyone else go there?
I didn't say it.
Then it would have changed it.
Okay. Ladies and gentlemen, 2 more questions involving this. First and foremost, this is on your quiz. This question is on your quiz. It was on your lab previously, but... I'm sorry? No. I don't remember what the density is. But a very similar question. You can't remember 3.3. Although, who knows? There's a lot of numbers out there. Maybe I'll hit it just perfectly. Yeah, so this question was on your lab, and a lot of people just left it blank. A couple of people got it right, which is great. I'm hoping they just didn't search for the answers or call somebody who had the class last year. But yeah, this is important stuff, being able to use these vectors. Now, the question I asked at the beginning of the day was, is the block, or can the block move faster than it falls? In other words, can this density be larger or smaller than 10? 10. Do you think it can go up faster than 10 meters per second squared? What do you think the density of a beach ball is?
Probably not.
If you answered not very much, you're probably right. So let's use a density of, how about a density of 100 instead of 1/10 of water? Is that reasonable? Yeah, it's mostly air, this beach ball. So let's use a density of 100, and let's see what happens. All of this, the volume and the buoyancy, is going to be the same, right? So, I'm sorry, no, it's not. It's going to be a lot bigger because we have to find the volume. But the process is going to be the same. So the FB, for our new block, which now has a density of just 100 instead of 750, the FB is going to be 10. Well, we need to find the volume displaced, right? So the volume displaced is going to be 10 kilograms divided by 100 now. So FB is still going to be FG. The volume of the water, volume of the H2O is now 10 kilograms divided by 100 for the density, kilogram per cubic meter. What's the volume of a fully submerged 100 kilogram per cubic meter beach ball? How much? 10 divided by 100 is usually 0.1. Okay, so it's going to be 0.1 cubic meter. Again, a beach ball has a density a lot less than 100, but we're going to go with 100 because it's a nice round number. So volume of 0.1 cubic meter, and if that's the case, then what is the mass of the H2O? H2O still is 1,000 kilogram per cubic meter. It's a lot. It's a lot. Yeah. 100 kilograms. That's a lot. Keep in mind, guys, a cubic meter of water weighs 1,000 kilograms. The density of water is 1,000 kilograms per cubic meter. So if you have a tenth of, well, a tenth is like about this. If you have a tenth of a cubic meter, it weighs 100 pounds. Okay? Yeah, 100 kilograms, yeah. It's a very heavy, water is extremely dense. Yeah, anyway, so the Fg of H2O is what? 1,000. So Fg is still mass times 10, or 1,000 newtons. And this is where we get to the good part. If you had a beach ball that somehow weighed 10 kilograms, a huge beach ball, but the acceleration would still be F net over mass, which would still be Fb minus Fg over m, which would be, in this case, 1,000 newtons minus Fg, which is 100 newtons, divided by the mass of, not 100, but 10. How fast is it accelerating? 90 meters per second squared.
So if that hit me in the face, what exactly would happen?
You'd probably get a pretty good-sized concussion, depending on how fast it was moving ahead of time. Now, if you have something at 90 meters per second squared and it hits you like this, you'd be like, it doesn't have a lot of speed or momentum built up behind it. But there's these things, I'll answer your question in a second. There's these things that people sell. It's a wristband for divers, and the thing is about this big. But when it's this tiny little thing, but when they pull the cord, it inflates to about the size of a volleyball. But that alone is enough to get them to the surface about as fast as they would be falling. It gets them to the surface really fast, even though it just goes, inflates about this big, and just pulls them to the surface. You don't need a lot. You don't need a huge difference in density when you're looking at something that has almost no
That would be really
density.
cool to see, and I feel like it'd be really majestic if you're underwater and you
Majestic.
start to float it up.
You'd be like,
Yes.
up and away! Yeah. Okay, Gina.
Question.
Yes.
Where does the air from the plate that?
It's compressed, like in a CO2 cartridge in your paintball guns, or your BB guns. You see those little silver CO2 cartridges? It is actually that thing that's actually powering it. So it's reusable.
That's good.
Yes, they do.
So
That's right.
second question. On this one that FG minus FB, like why is it switched up there?
Because this one we're talking about something, it's actually the difference between the two. This thing we're talking about something that is accelerating upward. That thing we're talking about something that's sinking downward.
All right, thank you. All right, that's my question.
Sure, you can take a picture whatever you want. I have one more question for you considering this before we move on to something else. And that question is this. Does mass play a role? In other words, if we took our 750 kilogram per cubic meter block, we had a small block and a big block, would they both accelerate at the same rate? Think about that for a second. With what you see up here, would they both accelerate at the same rate? Small block with the same density as big block, would they accelerate at the same rate up into the water? So I'll let you guys discuss it for about a minute while I make some room on the board.
I don't know, because I'm going to change that energy, obviously. I'm going to that energy. I'm going to do the same process, but with a different.
When you change the mass, you just change the source. Density remains the same.
If it's the same density, that means that.
Good.
Yeah, I was gonna say.
You just,
Good, I'm like, to what?
you just got his head hurt because he's thinking too hard. You just got to burn through that tumor. Just fire those neurons and burn right through that tumor.
Burn through the tumor.
Burn through the brain tumor.
Is this how we cure brain cancer, just by thinking?
Okay, let's think about this. The question was, does the mass play a role? Does a bigger mass have a different, does it larger or smaller or the same acceleration? Who says with a bigger mass, the acceleration will be larger? Raise your hand. Okay. Who says with a bigger mass, the acceleration will be smaller? Okay. Who says with a bigger mass, the acceleration will be the same? Figure this out. Okay, so let's take our original 750, and instead of 20 kilograms, what do you want to make it? I'm sorry, instead of 10, what do you want to make it?
6.
What?
You want to make it smaller?
No, bigger or small?
20.
It's up to you. 20,
20 kilograms.
25? 20.
20.
5. Let's use math that we can do. Okay, so 20 kilograms. Guys, all the math, the same process is the same. The volume of the H2O is once again mass over density, so now it's 200 over 750. Like I said, it's 20 kilograms over 750. So what's the volume of the water displaced? .0266 repeating cubic meters. So we've exactly doubled the mass. Are you guys comfortable with this? You want to use a different mass? Okay. So that's the volume of the H2O. Again, the volume is still coming from mass over density. Mass over density. Okay? So this is the volume the block occupies, mass over density, which is 0.0266 cubic meters. Then we need the mass of that H2O that's displaced. So we displaced this much volume. The mass displaced is once again density times volume. Okay? Density of water is still 1,000. Volume is 0.0266 cubic meters. So what is this? 26.6? Okay. So 26.6, repeating, cubic meters? No, kilograms. Kilograms. So far, so good? Continuing the process, I promise this is the last time we'll talk about this crazy plastic block. We'll do something else in a little bit. FG of the H2O is what? Mass times 10.
No, wait,
This is our kilograms. Turn it into weight. 266 newtons. And the fun part, again, the weight process is still mass times 10. And the fun part is the F net is still FB minus FG. FB is the weight of the water displaced. It's still 266 newtons. FG is the weight of the thing. What's the weight of the thing? 200. So the F net is how much? F net over m, which is 66. And what is the mass? 20. So the acceleration is?
3.3.
Who said same? It should make sense, right? Because it is the same. And if you're really exotic, you can actually do the math without even doing the math. You can just do the variables and watch how the masses just fall out of the equation. It's pretty slick. Okay. I hope you learned something. Now I have another question for you. And here's the question. Consider a ping pong ball. Here's a ping pong ball, and it's connected to a spring, and the spring is connected to a mass. The mass is just there to sink it to the bottom of the graduated cylinder. Hold on. He's in my last class. This is like Jesse, William Irwin.
Yes.
Yeah, Jesse. He's in my last class. So go fish. So the weight is there, basically there just to keep the ping pong ball at the bottom of the graduated cylinder. So what I'm going to do is I'm going to put this into the bottom of the graduated cylinder in just a second, and then we're going to answer this question. But before I do, I want you to look at the spring stretch. Okay. What's pulling the spring down? The weight. When I put this into the water, is it going to stretch more, less, or the same? Okay. Why is it going to work less? Yeah, because the buoyant force is going to basically take some of the spring force's oomph, if you will. Okay. So right now, gravity's pulling down, spring's pulling up. Buoyant force will also pull up and shorten the spring. Let's see if you're right. You can see how much it's extended now. Down you go. You are very much right. Less stretch. Okay. Unstretched, the spring is 5 centimeters. Stretched, the spring is 11 centimeters. So there's a difference in stretch, here denoted by delta stretch, of 6 centimeters or 0.06 meters. My question to you is this. Consider a ping pong ball submerged and held underwater by a spring. What is the spring constant of that spring? What is the numerical spring constant of that spring? What do you need to know? We know the spring is stretched 6 centimeters. What else do you need to know? But we're going to ignore the mass of the ball. The mass of the actual thing that's holding it to the bottom we don't care about. And we're going to ignore the mass of the ping pong ball because, honestly, it's a ping pong ball. Yeah. You do need to know force, but what do you need to know from me? What do you need to measure before you calculate things? You need to know the amount of water displaced, and for that, you're going to need what? The volume of the ping pong ball, which, assuming it's a regulation ping pong ball, the diameter of a ball is 40 millimeters. Okay. So the diameter of a regulation ping pong ball, diameter is 40 millimeters, which means the radius is what? 20 millimeters, or 0.020 meters. And who knows the formula for volume of a sphere? Good. 4/3 pi r cubed. Volume of a sphere is 4/3 pi r cubed. The radius is 2 centimeters. You now have everything you need to know to figure out what the spring constant is there. Same as before. Winning team, in the very, very short amount of time we have, gets cookies or fruit snacks. I'll give you a huge hint. It's less than 100.
Okay, so we have 1 out of 100.
That's like the nuclear bomb.
have an answer, put your answer up front.
I don't have to do it. Or any rewards. Do it, Haley. Do it.
Oh, I forgot mine.
I want to hear it.
I'm not gonna lie. I forgot mine.
Hear it about everything.
Keep in mind, the spring constants of the springs in your car are in the thousands. The spring constants in the spring in your pencil are less than 1. It is muy poquito, as they would say south of the border.
We're done. No.
I would use standard unit, 2 meters and kilograms.
Am I really?
Less than 100. Yeah. Remember, Hooke's law is F times X, Newton per meter. Is that a 5? Leave us and Braden. Leave us. Don't give up.
That's the right answer.
I'm sure there's plenty of places I can go and.
I found a job. I don't want it's a bad job.
Yeah. Oh, they're paying me. I don't know how much they're paying me, but I go to the store and I open up my wallet and let them take whatever they want.
I don't feel.
But Mr. Flyers, when I do that, there's nothing in there for them to take.
Me too.
They just
Take
keep me
care
out
of
of
all
the store.
my math problems and then yeah.
Like the guy, like the girl in The Bachelor who has a nanny, and she's 24. Okay, let's take a couple more minutes. Yeah. Doesn't matter. It's the mass of the object pulling it down is just providing an anchor. It is sunk to the bottom. So all we care about is the difference in stretch. The mass of the thing pulling it down is just an anchor, anchoring it to the bottom.
Oh, well, that.
It should make sense because there's only 2 things going on. There's one vector pulling down and one vector pulling up. What's the vector pulling down? We're ignoring the weight of the ball itself. The thing pulling down is the spring, and the thing pulling it up is the buoyant force. There's only 2 vectors we care about. Spring down, buoyant force up.
Okay, in that case, I have.
Those are about the same?
335.
Same?
335.
Yeah.
It's not too bad.
10% more strength, or 10% more money,
because of force.
or 10% better looks?
I mean, since I'm mean, that means I get marginally better.
You want 10% more sleep?
That's marginal. That means I get like, what,
Okay.
5 seconds of sleep?
It's up to, all right, the correct answer is up there. Oh, you're going to write your answer up there? Cool. What did you get?
What?
Fair enough. So yeah, the correct answer is up there. Let's work this out. Okay, so KX is Hooke's law. Hooke's law tells us about the force that's pulling it down. And guys, since the ball is neither accelerating up nor accelerating down, then we can say those two forces are in what? Equilibrium. Good. So we can say the KX force down is equal to the FB force up. FB is still weight of the water displaced. So to get the weight, to get the weight of the water displaced, first we need the volume of the water displaced, then the mass of the water displaced, then the weight of the water displaced. So the V of the H2O is 4/3 pi r cubed, which is 4/3 pi 0.02 cubed. I don't know what that is. What is that?
0.00008, or 8 times 10 to the negative 6.
8.0 times 10 to the negative 6? Sounds great. So that's the volume of the H2O displaced, which should make sense because we're talking about cubic meters, and that's a really small volume. Okay? So if that's the volume of the water displaced, then what is the mass?
That's not correct. That's right. Hold on.
Oh, hold on.
That
Hang
was
on.
0.02 cubed. I thought that's what you're asking. Never mind. It's,
Times pi times this.
It would actually be, let's see, 3.351 times 10 to negative 5. 3.351 times 10 to the negative 5.
3.35 times 10 to the negative 5 cubic meters. Okay, so the mass of the H2O is going to be the volume, just like before. Mass is volume times density. So the mass is 3.35 times 10 to the negative 3.35 times 10 to the negative 2 kilograms. And that means the FG would be 3.35. I really hope you did the math right. Times 10 to the negative 1 newtons. Cool? All right. So let's take this relationship, move it over here. That means K is equal to 3.35 times 10 to the negative 1 newtons over X, buoyant force, divided by X. X is 0.06 meters. Is that right?
Yeah.
So what's the answer? Yeah, about 5.6 Newton per meter. Yay! You guys want some more treats? Okay, give me the Leafus and Braden. Do you want cookies or fruit snacks? Okay.
Was that violent cap there last year?
Yes, it was.
I'm sorry, what's that?
Was that violent cap there last year?
Yes, it was.
I think that's the first time I've ever seen you open it.
Ever since we had to move all the chemicals in the back storeroom, I need to have something I can lock. Okay, so one more question, then we're done for the day. This is actually a lot of fun. And we got to go kind of fast. The question is this. I'm going to take my ping pong ball and spring out of water and put it into isopropanol. Isopropanol, if you remember, has a density of 800. So water is 1,000, isopropanol is 800. When I take it out, oh, by the way, right now, the top of it is sitting at about the 610 milliliter line. So I'm going to take it out and I'm going to put it in here. What I need to know in the next 3 minutes is, will the spring stretch more or less? Alcohol is less dense. it was at 610. I'm going to put it in here in just a second. Into the isopropanol. 800, 1,000. Okay. Have you made your decision? If you think it's gonna, you think it's gonna stretch less, raise your hand. Yes. If you think it's gonna stretch more, raise your hand. Wow, about 50-50. What is causing it to pull? What's causing it to pull down? Gravity. In this case, gravity. But when I do this and the water's pulling up, what's causing it to be small? The spring, right? Is the spring stretch going to change? That's ultimately the question we're talking about. Well, the spring stretch is going to equal to the buoyant force, right? So if the buoyant force goes down, should the spring stretch go down? And it does. It was at 610, now it's about 550. Why did the spring stretch less? The buoyant force was less. Why was the buoyant force less? Because the density of the fluid was less. Does that make sense? Remember that? Okay. Buoyant force depends upon the density of the fluid. It is the weight of the fluid displaced. So if the weight is less, the buoyant force is less. If the density is less, the weight's going to be less. Questions?